You can find me on the internet at ChrisJRN. If you're on the Mastodons, there's my handle. I needed to correct a thing from the keynote. There's a San Andreas fault. That's where I live. As you can see, nowhere near it. So anyway, I run the North Bay Python conference in Petaluma there. If you're ever in the area in like April, you should come along. It's a lot of fun. But when I'm not running Python conferences, I also give talks at Python conferences. And over the last 5 or so years, I've been giving a lot of talks on sort of the history and philosophy of Python and why Python is the way that it is. And whenever I give these talks, I go in with a plan to write talks and talk about interesting, unique things every single time. And every single time I do, I end up accidentally talking about decorators. And so for this year's talk, I've decided to do something different. I've decided to start by proposing a talk that's actually about decorators and seeing where I end up with that proposal. I'm not too interested in discussing ethics, religion, or philosophy. What I will tell you... Calm down. What I will tell you is that this talk is going to start relatively basic, and it's probably not going to end up relatively basic. That's so that we can cover a lot of ground. I'm going to skip a lot of irrelevant details, which means that if there's a detail you've noticed that I've skipped, it's irrelevant. So, first, a very quick recap of what a decorator actually is. We all know what a decorator is, right? So, say you have a function which does something obvious like this. When you call that function in Python, it will do what you wrote in the function. So you've written a function that prints I'm a banana. It prints I'm a banana. Decorators, these are these statements that begin with an @ symbol before the definition statement, are Python's way of providing a structured way to do something with functions, methods, or in later versions of Python, classes. So adding this surprise decorator here makes our function print a new thing before it executes, which is a surprise. This is how that decorator works. Our decorator takes that function as a parameter, it creates a new wrapper function, and it leaves that wrapper function in the place of the function that we originally wrote and named. So to be more clear, when we put that decorator statement before the function, once you've defined the function in your code, Python will pass that code block to our decorator, which is a function. That decorator is going to do some stuff, and then it's going to leave that new function that it returns in the place of our original function. Okay? So, a decorator is a function that takes a function and it leaves a function. Is that correct? No. It's not. So let's return to this original decorator that we wrote. So under the hood, our modern Python decorated function, this is a bit above the dashed line, it's doing the same thing as our more ancient Python decorated function, and that's this bit at the bottom here. And so what's going on here is that the bit after the @ symbol in the top, that's actually an expression that when evaluated gives you a decorator function. And that decorator function is what gets called, and that gives you the function that we were trying to decorate here. So if you wanted to add a parameter to the decorator, you could do it like this. So you have a parameter, and you end up with a function that's nested 3 deep, which is a lot more confusing than the 2 deep functions that we saw earlier. So you make a function that takes those parameters that we want to use in the decorator statement, and that's going to return a decorator function, like we're doing here. The decorator function accepts the function that's going to be decorated and will return our wrapper function, and the wrapper function calls the function that we defined under the decorator expression. It's very, very confusing, right? But it's a lot easier to remember if you remember how the Python code with a decorator translates this more sort of manual, old school type Python code. It almost makes sense if you're paying close attention to it. So, a decorator is an expression that is itself a function, which itself takes a function and returns a function. Is that correct? No. And it's not correct because a decorator just literally assigns the result of the decorator function to the name of the function that's passed in. There's actually no requirement that value be a function. In fact, there's no requirement that thing be anything at all. And that seems really confusing for things that should just be modifying functions because you've used this def statement and def means there's a function there. But it at least explains to us that a decorator is a value or an expression whose value is a function which takes a function and And that's why I've spent 5 minutes defining what a decorator is. It's really quite hard to define, quite hard to wrap your head around. But on the other hand, decorators are weirdly flexible and they unlock a lot of unexpected and useful design patterns in Python that aren't really accessible in other ways. So they all come from that observation that Python doesn't say what a decorator actually has to do with the code that you choose to decorate. So that's what today's talk is about, this here giant pile of question marks. So for the rest of today's talk, we are going to look at why Python got decorators in the first place, and what decorators enabled in popular libraries and frameworks, and then we're going to finish off with the fun stunt bit where I do weird design patterns that you probably shouldn't be using. Okay? Okay. So first up, we are going to look at how Python ended up with a feature that is, on the face of it, a lot more complex than it needs to be. So Python has always been an object-oriented programming language, but on the other hand, a lot of people who worked on Python had come from languages like C, which are very much not object-oriented. And what those C developers liked was that it was possible for multiple people working within a code base to be working on different files to be able to name their variables and their functions the same thing, and not have to worry about consumers accidentally using the wrong function. The Python feature that enables this is called namespaces, and namespaces were a thing that early Python developers really liked. And the way we did namespaces in the first place was with modules. And that's really not a very flexible thing. It allows you to define namespaces based entirely on your file system structure. So in math, you can have a function called log. In logging, you can have a function called log, and these are different things. And generally speaking, we know that having namespaces corresponding entirely to file system structure is not very useful. So what's the alternative? So say you have a class that pairs a name and an address. So Python gives you the ability to create one constructor, and so you make a class, you make the fields, the parameters, but in practice though, you might be like taking a serialized object like a JSON dictionary or something, or it's the 1990s, maybe it's an XML file or something like that. What you'd need to do is create something called a factory function. And a factory function is a function that lives in a module next to the class that you want to instantiate. And that's going to do the jobs of pulling the parameters for the constructor out of that serialized form. And this factory function thing is not great. You can't really namespace things intuitively. It's only the name of the function that makes it clear what we're going to get from that factory function. And so just like C, we need to use really long, redundant, non-clashing names to make sure we get the uniqueness and we get the names right. Because if you have more than one class in the same module, well, you need to make sure the names of the corresponding factory functions don't clash. And it's a code organization nightmare, and this is exactly why we like namespaces. And because this was the late 90s, early 2000s, Python looked to the world's source of inspiration on code organization at the time, which was, of course, Java. And Java has some really firm ideas about how code should be organized. One thing that allows that Python would never allow was multiple constructors. No, Python would never allow multiple constructors. But there's one thing that Python could borrow. It has this concept of a static method, which is a method that gets called on the class itself rather than on an instance of the class. And it has this as a first-class language feature, and one thing it allows you to do is to organize your factory methods underneath the class where they logically belong. And this would have been something really nice to have in Python. So when Python 2.2 was released, it added a fancy new feature. You could define yourself a method inside a class, and then after you defined that method, you could say, oops, this is a class method, and let's make this a thing that lives on the class and not on an instance of the class. So class method and static method were two ways that Python decided to do more namespacing. And this was a way of defining something as a class method, without using a new language feature to do it. This was called the decorate pattern, okay? And with a decorate pattern, people were really happy that they could start adding namespaces to their code. Wake up. Okay, so this pattern, by the way, is something I'm going to come back to a lot in today's talk. I'm going to call this define, consume, and throw away. Define, consume, throw away is sort of an anti-pattern in most other programming languages, but it's something that we, as Python developers, reluctantly accept. And as I was saying, Pythonistas actually discovered a problem with this original decorate pattern, which is that if you have a really, really, really long method, so long that it goes to the end of your screen, then it becomes really difficult to notice that the method you've defined is actually a class method. And this is a case where it became quite difficult to read Python code and understand what was going on at a glance. And we, as Python developers, really value readability. So we got this thing called PEP 318, which had a really catchy name of Decorators for Functions and Methods. And this came up with some goals for inventing a new language feature that would make decoration a much easier thing to approach. And if you're interested in reading some historical documentation from Python, this one's a fascinating one because it tells you what people were thinking in the early 2000s about what Python would do. The idea that there might be a JIT compiler at some time. Python 3.14 is adding a JIT. But also, it observed that decoration was hidden and it really needed to be moved to the front of the function where it's more in your face. And so decorators, as it turned out, was a really interesting feature. It turned class method and static method into something that was easy to use and people would want to use for namespacing, rather than something that's awkward, and it started making other ideas in Python a lot more accessible. So second idea of object-oriented programming is encapsulation, as this idea that a class has the ultimate responsibility for its data. So back in Java, the way that you ensure that data is controlled is to make sure that the data fields themselves are private, and then we gate the access to that using a method. And so if you need to change an implementation detail, you change the method. And so there's no difference between a stored property, that's one where you just return the value, and a synthetic property, which is one where you do some calculation before you return it. So Python never really had private fields, and so it never really discouraged people from directly accessing fields in objects. And so by convention, this means that there's a visible difference between stored properties, that's like filling in this case, and the synthetic property. One you have to call as a method, the other you don't. And the problem with this is that it makes it hard to change from a stored property to a synthetic property. The people who consume your APIs need to change how they access things. And so Python invented another decorator called property, and this actually came around at the same time as class method and static method. But unlike class method and static method, people didn't use it immediately because it was really awkward. So if you have a class that has some stored properties and some synthetic properties, by replacing the getter method with @property, you can access the synthetic and stored properties in the same way. And yeah, it lets you refactor from a stored property to a synthetic property without breaking compatibility. You don't need awkward setter and getter methods, nor do you need to know if a property is stored or synthetic. What's interesting about it, though, is that it doesn't return a function. It returns a thing that you access like a variable that you don't need to call, which is why decorators are as flexible as they are. So even though it's changing the semantics of these things that look like methods when you define them, it's much clearer to the calling context what it is you have to do with them, because it's not enforcing that a decorator has to return a function or a callable. So this decorator syntax, it immediately caught on, and plenty of languages have stolen it since. And yeah, it's also interesting because unlike the decorators that we started off showing, there isn't actually any wrapping going on behind the scenes. Python uses descriptors under the hood, but this is a sort of easier implementation to understand. Properties sort of works by adding some magic inside the internals of classes, and it intercepts attribute lookups in your class. And so the decorator just needs to do enough to tell subsequent calls to get attribute the thing you're defining as a property. And this is all you really need to do. Like, the implementation with descriptors is a lot more complex, but the seeds are there. You add some interception code, and then you add a decorator that leaves that information that the interception code can pick up. And this decorator that we wrote has the same basic effect as Python's property getters. And so decorators and Python's model, where you can access the internals of a lot of parts of the language, mean that you can really alter the semantics of the language to make your libraries easier to use or more powerful. And that's meant that decorators have been used in a lot of interesting places throughout the Python ecosystem. They're there in the standard library. FuncTools has a bunch of them. I think it's worth calling out Django here, because Django realized that decorators are a really useful way to apply frequently reused code to functions, like require HTTP methods, which gives you the wrapper code to reject things, HTTP methods that aren't applicable to a given view, and you don't have to remember to write the boilerplate code. Django uses decorators all over the place. There's a bunch of classes that have emerged since then, but I still find myself using their decorators all the time. It's made this really good observation that sometimes there are structured and repetitive behaviors that fit into pre-call and post-call parts of a function. And these are much better suited to this wrapping approach rather than using mix-ins or other object-oriented behavior. So we've seen why decorators happened. We've seen why they brought in the things that they brought into the world of Python. We've seen post-processing. We've seen techniques for code reuse. And we've seen ways to selectively add improved semantics without needing to add new language features. But these aren't the only things that decorators let you do. So I want to show you how some decorators open up a way to solve problems that other languages have solved with features like anonymous blocks. Some of these things are things that I've thought and talked about in the past, and some of these are new and you may not have seen them before. I'm not convinced that any of these things are actually a good idea, though. The only thing that I want to convey here is that these are cool things that you can do in Python, and they might inspire you to write more interesting code and more understandable code if you spend some time thinking about it beyond the contrivances I'm going to show. So the first thing I want to talk about is this idea of a scoped block. This is something I touched on in my 2019 talk on anonymous blocks. But when I wrote that, I really didn't have a good solution for Python at the time. So one of the things that blocks help with in languages like Ruby or JavaScript is with maintaining variable scope. So that any given block of code doesn't depend on variables that are defined further inside your code. And my thinking around this came actually on my time working Kotlin. And Kotlin has this philosophy that everything is an expression. So if you have a web framework, for example, that needs to produce either a user response or an error response depending on the contents of a request, you only need to define this response variable once. So you only go response equals the one time there. So if it's a user here, the response is assigned the user response return. If it's an error, it's assigned the error response. Hey, so that's reasonably easy to follow even if you don't understand Kotlin. And this actually looks reasonable in Python as well, if you don't need to deal with error handling, okay? Once you do need to deal with the error case, well, you need to handle the error, and you sort of have to define this response variable inside two different inner blocks. And then you need to handle that response variable in the outer block. It's not very nice, it's quite easy to make mistakes, and there's a whole pile of Python tools, like including MyPy, that really don't like this pattern of code. Like in MyPy, you'd have to define the variable beforehand. It's not pleasant. So one way to refactor this is to pull that if statement out as a function. And so now our original function has the same structure as the one that doesn't have error handling. You see, we're only defining response once there. But now you have to divert your gaze. When you get to the response line, you have to go down to this function that we're writing, and then you have to look back up to figure out the control flow. And this is what I call bad visual locality. It also gives you a new function that's visible. You may need to support that, even if you intended for it to only be a private function, even if you only intended it as a one-off helper for the bigger function that you've written. The alternative is to put the throwaway function in line inside the original function. This is better for visual locality because you can see where the code block belongs. You don't even need to pass a parameter in at this time. What's more annoying is that you still have this define, consume, throw away behavior. You're writing this function just so you can call it once and you can keep the result. But that's not clear at a glance until you read the entire body of the function. So you need to read everything before you understand what's going on. You know that at some point, this thing that I'm defining here is going to get called, but you don't know when until you've read the entirety of the function. This is something a decorator can solve. And here is that decorator. Have you understood it yet? Okay. So all it does is it calls the function that we're decorating and it returns its result. So in practice, you define a function that takes no parameters and it returns something that you want to use in a variable. You put the run decorator before you define the function, and then magically you end up with a variable instead of a function, okay? So this is useful for our branching block that we were looking at earlier because we can go from using define, consume, throw away to defining our variable by using the run decorator. And so this gives us the advantage of scoping our variables properly. We define them at the level where they'll be used. We get the scoping benefits of a single-use function, but without the poor visual locality of define, consume, throw away. Okay. The next thing I want to do is look at the idea of stream transformations, which is something that Python is actually quite strong at already. Except, if one of the transformations that you want to apply needs multiple lines of code to write it effectively. Python has, for the very longest time, avoided having multi-line lambdas. And this pattern it's one that's going to let you take advantage of multi-line lambdas. So, a stream transformation is something along the lines of a list comprehension or a generator expression. List comprehensions and generator expressions make a lot of sense when you only call a single method or you can call a function that already exists on your input iterable. Or if you can string from one transformation to another with minimal branching. But if you have something that requires branching, here's a common one, that's when things really start to get awkward. This is a variation of that define, consume, throw away anti-pattern, which, as we know by now, it's not a very good thing. So, especially since other languages, including Kotlin, Swift, some others, have begun to figure out that if you have a lambda expression as the last argument inside your parentheses, there's alternative syntax that lets you pull that lambda out and place them outside the parentheses. So, if you combine that with if expressions in Kotlin, for example, you end up with something that's quite elegant for this programming interview problem. Okay? Now, we can't really get that list comprehension into a nicer syntax than this in Python. This is sort of the limit of list comprehensions. But we may be able to do something with our legacy map function. Okay? So previously, what we'd do is we'd define our multi-line function. We'd call map using that multi-line parameter as a function. That's define, consume, throw away again. So let's use a decorator to get that map call up the front so it's clear that what we're doing is defining a function that's going to be used as a parameter for map. So let's define a decorator called apply, which takes a transform function like map or filter and an iterable, and then accepts a real function as the thing that's going to do the transform on each element. And then you use it like this. You say apply map to items using the function that we're about to define and then store it to the output. And with that, we can take our define, consume, throw away code and turn it into something where we say what we're going to do with the code before we define it in exactly the same way that we would with a lambda expression.
I hate this less than the last one. There's also a syntax error.
Hey, so that's a couple of patterns where you can use decorators to avoid this define, consume, throw away anti-pattern. The next thing I want to talk about is the builder pattern, which is actually well established in the Python community, but the way that we use it in Python is kind of ugly. So a thing that we like in Python, we like writing out our data structures in code, but there's only support for a small number of officially blessed data types in Python, your lists, your strings, your dictionaries, your tuples. Builders are a way to create data structures in a way that isn't restricted to what the language provides. But in its usual form, there's a lot of repetition, and there's this side problem of defining the thing at the top, but you don't show how it's going to be consumed until much, much later in the process. And indeed, the first things you define here are the last things that you consume. This is not so much an issue for this reasonably flat data structure that fits on a slide, but as things get more nested, and this is a nested data type here, this lack of clear visual locality becomes quite difficult to deal with. But generally speaking, builders are almost always used like this. You create the builder, you do some things that add data into the structure that your builder is creating, and then you build it. So we can do that to build up a data structure like an HTML document, for example. So here's a class called HTML node builder. It takes a tag name when we initialize it, and it has a build method that puts everything together. But here's the interesting thing. This is a node method. It's actually a decorator that will create a builder. It's going to pass it to the function that we're decorating, and it's going to build the builder once the function returns. And then we just need to create one more decorator to string everything together here. And then suddenly you end up with a function that defines an HTML document. But more importantly, it has a structure of the document that we're creating. It strips out all those repetitive calls to create a builder and to build the build, and it also builds the builder. It just leaves us the task of writing out the data structure that we want to use. Now, unlike our previous patterns, this one encourages you to write more functions, but in doing so, you end up with the code where you interact with the builder, and you interact with it with much less boilerplate. Okay, I understand I have less than 5 minutes now, so I'm going to wrap up. That is the end of this whirlwind tour of decorators. We've seen what decorators have allowed us to do in Python, and we've looked at a few design patterns that show some unexplored ideas that might be enabled by decorators. The first is the idea of throwaway functions. They're not the same as truly anonymous blocks in languages that offer anonymous blocks as a first-class feature, but decorators definitely enable the closest thing that we have in Python. And a lot of the patterns that other languages use with anonymous blocks can be approached with decorators if you want to use them appropriately. We also saw that decorators are great for transforming functions into the data that they produce. And this is useful for programmatically building up these data structures. And we saw how the really quite complicated and awkward builder pattern can be replaced with something that is a bit more readable. So that's it. Thank you all for coming along. I think there might be a small amount of time for questions. So
we have time for maybe 2 questions. Fine.
Firstly, why? And secondly, does MyPy choke on? Does it give, if you try and type such an abomination, does it give you useful hinting output, or are we in the prehistoric times as far as typing goes?
Python will deal with type hints on decorators. So if your decorator function says that your decorator is going to return something that's not a function, MyPy will deal with it just fine. So you can do all of this with modern typed Python. This is everything here is not unreasonable Python to write from a technical perspective.
All right. We have time for
and the first question, yes.
We have time
That's
for one more. Someone at the back, if you want to really test Amber's overhand skills. Maybe?
No more questions?
No more questions? Awesome.